I just want to briefly recap what we did last time. So we started and then talked about universal approximation, which is just a qualitative statement. From there, we went to approximation rates, and we discussed how shallow networks can approximate infinite width networks. And then as a second step, we also discussed briefly about how to derive approximation rates if the target function is not an infinite width network, but just some function in here defined on the sphere. And the surprising thing that I tried to convey was that the saturation that we typically see in approximation theory, that if we take a non-smooth class of functions, candidate functions, to approximate a smooth class, that where typically you don't get the good rate, which is beta over d, that this happens much later for shallow networks, because for shallow networks it's not the smoothness of the activation function, but the smoothness of this integrated version, the infinite width networks, that matters for the approximation rates in the end. And so they are smoother than, because you integrate, they are smoother than the activation functions itself. And that gives, in the case of value, that gives you this d minus 1 over 2, because you basically take d minus 1 integrals if on this sphere embedded in d dimensions. Okay. And then so we discussed a bit like this harmonic analysis that underlies that thing. And I just want to go back to this. I added one more slide because I think now I can make it a bit more clear. This is based on another course which has had twice the length. So I shortened it and I kicked out some slides, which was not very smart. In particular, this thing, I believe this is quite important. So how does it work, the whole approach? The whole approach works as follows. Like, we have target function that we want to approximate with our shallow neural networks, and this one is called G. And harmonic analysis allows us to write it as a sum and then project on these spherical harmonics. And we can do the same with the infinite width network. And if we do that, then we can write it in this form. And the nice thing is that if we have this infinite width network has this convolution type property that the projection of the f factorizes into something that only depends on the activation function, and the other thing only depends on the phi. And what is the phi? Right, in this case, we say that f actually has this representation of sigma w transpose x d tau w, where tau was the uniform measure on the sphere as d minus 1. Okay, so then we have this, and now we can pick our phi such that this function f approximates the g. One way to do it, to pick the phi via its projections, and we can, for instance, choose this rule and take for all the frequencies below capital M, where we can tune M later, we can pick the projections to be just that, because then if we stick in this formula, then the sigma hat k's, they cancel out, and we get exactly projection k d g exactly as here. So then they match. And for the higher frequencies, we just take 0. Then we have this Parseval identity that says that the L2 norm, the squared L2 norm on the sphere is just the sum over these squared L2 norms of these projections, which means if we choose the phi in that way, and then compare and subtract these two formulas, then on the first frequency, they have the same projection. So this is 0. And only on the frequencies where we cut off and we take this to be 0, then we are left these projections. And so then over all the frequencies above M, we have to integrate and take these squared L2 norms. And for the phi thingy, because we have chosen it in this way, the high frequencies are 0. So we only have to deal with the low frequencies up to k equals M. And in this case, we just stick in this. So this is a number, so that we can pull that out of the L2 norm. And that goes then quadratically because it's squared. And then we have in here, we have this one. And now the thing is, how do we pick the M? The M we pick in such a way because the whole approximation is that we want to approximate G by a shallow network. This approximates G by an infinite width network. And we had also a bound how to approximate an infinite width network by a shallow network with M units. And so if we invoke this bound, then we see this bound depends also on this quantity here. So that means to make this bound not too large, we don't want this to be large. On the other side, we want m to be large to have this small. So there's a trade-off. So if you make m very, very large, then this one becomes small, this one will become large, and then this approximation error will become large, and the other way around. So we can later in the end, depending on what this class G is, right? Smoothness of G will translate into decay properties of these coefficients, like in Fourier analysis. So the smoother the G, the faster the decay of these numbers. And that will matter then on how to optimize the m, what the m is. And if we do that, we get to approximation bounds for really approximating target functions, which are not infinite width networks, by shallow networks with m units. Okay, so that's the overall strategy. And this is the paper, because you asked us on Monday. So that's the paper where this is described, and I just try to give you a high level overview about the idea. So this is the thing, is this delayed saturation. Now the final thing I want to discuss about approximation rate before we then come to more additional and properties of depth. Approximation rates for shallow networks is these Barron classes. Historically, they are became much earlier. So there are two papers by Andrew Barron in 1993 and 1994. And so the 1993 paper basically uses this Morris theorem that I mentioned in the last lecture. And that gives, in the simple form, it gives the 1 over square root of m rate, right? We have seen that, and you can even improve that. We have seen that you can improve it for, say, values and other, depending on the smoothness of the sigma and the dimension of the parameter space. And there's also what we had before, the kernel phi. And here, in Andrew Barron's work, he takes a specific limit such that this phi, this kernel function phi, what we had on the previous slide, this one becomes now replaced by this number, where we take the Fourier transform, and then in the Fourier domain, we multiply with the L1 norm of the frequency and integrate this out. So this is the bound. It's dimension free because there's no d in there. Of course, the CF can depend on the dimension. And in particular, and there's also d over here, and it has this 1 over square root of m rate. And based on this result, people had said neural networks, and that's still something on, like I see from time to time, neural networks can avoid the curse of dimensionality, and that has to do with the fact that this rate m does not deteriorate. It's always 1 over square root of m independent on the input dimension. Okay, so this part does not deteriorate in the input dimension, and so why is it now a question for you to get started? So why doesn't that avoid the curse of dimensionality?
Because the CF might depend on the explanation.
Yeah, but how? Yeah, that's good. That's correct. Yeah. But how does it? I mean, what's the so the thing is, right? If we have smoothness, if you have a function f, and this function f has smoothness beta, and it lives on the domain. It is defined on the domain 0, 1 to the d, say. So then we know that the rates, these approximation rates, if we take n parameters, is n to the minus beta over d, right? This is the thing from the last lecture. This is n is the number of parameters, which is basically here m times d plus 2, right? In a shallow network, the number of parameters is n, and then for every of this ones, there's here d, there's 1, 1, so d plus 2, m times d plus 2, so n is m times. But why don't we get to see something like this? And so how is that one encapsulated into the constant CF? You have an idea? Or you even understand my question?
No, I didn't.
Okay. So we would expect something if we have smoothness beta, we would expect this rate. And so if beta is, say, 1 or so, then we get the rate n to the minus 1 over d, and that suffers from the curse of dimensionality. Now, in this Barron approximation result, we get the rate 1 over square root of m, which does not, this one does not depend on something like 1 over d or so, right? So that doesn't have this curse of dimensionality thing, which is in this typical approximation rate. Now, you said correctly, this is somehow baked into the CF. But the question is now, how does it, what's the thing? Or how is that seeming like there seems to be a contradiction, but how is that built into the CF? So the thing is, the CF is only finite if beta is something like d/2. Okay, so this means to have CF finite. Okay, that's not small zero, small infinity. That somehow means, and that's not exact, that the smoothness of the function has to be, sorry, not smaller, but larger equal than d/2 or so. Otherwise, this thing won't be finite. That's not entirely exact, but it's basically more or less the right thing here. Because if we have this, then this traditional rate n to the minus beta over d, this becomes n to the minus 1/2, right? And if we think about n is, okay, so we said for the shallow network, n is equal to m times d plus 2. But if we take d to be a constant, then all what matters is dm. And so then this is of the order m to the minus 1/2. And this is then exactly this rate that we see over here. Okay, so that's, okay, it's much more subtle than that, but this is essentially what underlies that. And then the surprising thing is that you can, here you don't see, if you write it in this form, you don't see that if the dimension of the domain increases, that this to be finite requires more smoothness. But it's again something because you integrate over a higher dimensional space here as well. And that means somehow you need a faster decay of the Fourier transform in order to have this, and faster decay means more smoothness on the function f. And that is a bit like, because it's so implicit in there, you don't say this has smoothness, because now the smoothness grows with the dimension itself, right? So then we can overcome Grashof dimensionality. And so that's basically the rationale behind that. And there's nothing specific about neural networks in particular. I mean, the neural networks, what I mentioned before, is they can do one more thing which normal, like traditional statistical methods cannot do. They can also do this feature learning in here, right? So we have a linear combination here and this in the outer layer, but they can also, because they can adjust these double J and Vj, they can do the feature learning. But for this Baron class, feature learning is not crucial, because if you look into Immanuel Kant's PhD thesis, for instance, he just shows for the same problem, you can just by Fourier series, and Fourier series, the frequencies are fixed, so they're not learned. So there's no feature learning involved. And then you just truncate off the high frequencies. What we do, you can also achieve this rate m to the minus 1/2. And he also gets the minus 1 over d correction term, which we saw later that is, you can always improve that this Morris theorem, that is something we had this s over d and s is equal to 1 or so. And then you can get that rate also for Bern's result. You can improve it by this 1 over d. So basically they match. Okay. Now let me finally come to something statistical. In the second paper by Andrew Baron, 1994, he also considers statistical problem a learning problem. And I think I presented in the way he presented back then. Since then, we of course made a lot of progress extending the whole framework. But I think it's nice also for people who are not so familiar with these to see it presented in this historical setting. So what Andrew Baron does, he says, okay, suppose we have training samples and training samples. They are IRD independently from the same distribution. The inputs in RD and corresponding responses. So it's a regression model. It's not classification, it's regression. So that means the response is itself real valued, but it has to be bounded. These values have to be bounded by 1. That's a technical assumption. And then based on the sample, we want to learn the regression function. So this is the typical thing. So we want to learn the conditional distribution. Given that I have seen a certain x, what's the distribution of the y, or what is the mean of the y given this x? So that's the regression function that we want to learn, that is unknown, and that we want to learn by fitting a shallow neural network from there. For instance, this class of this problem of binary classification, in this case, yi is either 0 or 1, so that satisfies this condition. And then if you stick in that then this expectation becomes a probability, and you can just work it out, right? So it's 0 times the factor this is 0, so that drops out, and this is 1 times where this y times the probability of that, so this becomes just the probability of that. So that's an example, and then in this case, these objects are also called the a posteriori probabilities, or also the class probabilities. Okay, so now we have defined our objective. The neural network should learn this function. How do we learn it? Well, we don't do gradient descent. We just do what we call now empirical risk minimization. So we define an objective function, the least squares, like same thing also people in deep learning do. And then we just study the empirical risk minimizer. That means under all the, so we have a parameterized function class here, which not necessarily neural network, but neural network is a specific instance parameterized in a parameter vector theta, and the parameter vector lies in the parameter space capital theta, and that can be, for instance, the whole R. If we have d parameters, it can be the whole RD or so.
So just some question.
Yeah.
So the xi yi, the yi is some deterministic function of xi plus noise, or
that is one example. So if you're
not necessarily that.
Not necessarily. So in the binary classification, you cannot write it as an additive noise structure.
Yeah.
But if you, this is another way, like this, what we call the non-parametric regression model is also of this form. So if you have xi, and then we have independently sampled noise, say from a standard normal, then if you now work out what is the expectation of yi given xi, then you stick in here the sum, and the expectation of epsilon I does not depend on the xi, has mean 0, so that drops out, and then you get exactly f of x back. So that also has the property. And there are a couple of models like binary classification, but also the additive non-parametric regression model, which all fall into this more generic framework.
So if you have binary thing that, like, you toss a coin with a small parameter and you flip the
label, yeah,
label, something like that.
yeah. So you can see it like this, but you can also think about that there are, I mean, suppose you get to see this, is that the same thing? There can be also something maybe covariant dependent, which still has expectation 0. Yeah. In principle, also here, you could put in something like a sigma of xi in here as a variance term. And then still the whole thing would go through, because now if you condition on the xi, this becomes deterministic, and the expectation of this thing is still 0. And so this still satisfies this framework. And in this sense, there can be more. So you can maybe the probability, you can make it covariant dependent, and so there's more flexibility than that. Yeah. Okay, so clear. Other questions? Okay, so now, so what you then prove, what we nowadays we call that an oracle inequality, and this is the whole workhorse, but this is somehow a very basic version of that behind statistical risk bounds. So later, what we want to control is the generalization error, which is this one. Okay, generalization error is basically saying, okay, so we want to control like what happens if we get to see new x and we have to predict the corresponding y, and then if you work it out, then you come to quantities like this in terms of like what the expected error is in this case. Okay, so you have learned this f hat, and then you get to see a new example, and then you integrate out and you get some sort of weighted L2 distance here, or just the L2 distance. Now, these oracle inequalities, they show by using empirical process techniques and exponential inequalities and so on, they show that you can bound this statistical quantity, the risk of the generalization error, by 2 quantities, which are much easier to control. And they account for squared bias and basically some sort of stochastic error or a variance term. So the bias is just the approximation error, which we have studied a lot before. And so the thing is like how well you want to learn the function f, like how well can you approximated in this function class that you use as candidate functions in your least squares loss. Okay, so if you have a neural network and you somehow allow your flexibility, then you say, okay, so how well can a neural network approximate the function that's that underlies the data and the data generating mechanism. And on top of this, there's another term which measures somehow how hard to learn that, how hard it is to learn this function f from a statistical perspective. And so this has this 1/n thing because it's a squared rate. So you know that like in standard statistics, we have 1/n rates, but if we square this, we get to 1/n. And then the more parameters we have, the harder it gets. So the standard statistical variance term is a number of parameters over the sample size. And that's a sort of a proxy of that. This here behaves basically like the number of parameters because you have to discretize every parameter and then you get the power and then you take the log and in the end this becomes somehow the number of parameters. So it's a bound. I don't go into the proof. Yeah, so if you just look for Orca inequalities, and so you find proofs in textbooks and so on. Okay, so how is it then applied to get to risk bounds for shallow neural networks? Well, so the thing which nowadays, I mean, here he works with a discrete set. So you have to quantize your weights. You can't say continuous nowadays. We can do continuous weights as well in Orca inequalities, but it was 1994. So and how does he discretize it? He discretizes it exactly this way, how you would discretize it. It's so every parameter. So overall, this is the number of parameters in your shallow network, right? M times d plus 2. And then every of these parameters you discretize at a very fine grid. Let's say 1/n squared, and you go from n to the minus 100 to n to 100, and then you have this 1/n to the 50, say, discretization, so very, very fine discretization. That gives you then n to the 50 times n to the 100, n to the 150 discretization points for every parameter. And then the number, this cardinality is bounded, the cardinality here is bounded by n to the 150 to the power of the number of parameters, because you have done that for every of these parameters. But then you take the log, and then this n to the 150 just becomes log n, because the 150 goes just in here as a constant. So that means you can go very wide with the sample size n, and on the other side also discretize finer and finer on a like polynomial like scale 1/n to the 50 or so, and still just get a log n factor on top of the number of parameters. So the number of parameters is essentially what you would like to have in this bound, what I explained before for the variance term. And then on top of this, you always get like an additional log factor, which comes from the discretization. And now, if we stick in these bounds, we get here, okay, let's think about D to be fixed. We are just interested in the behavior in the M, which is the number of units in the hidden layer. And then for the variance term, we get here m times log n, so m times log n over n. So this was the second term here, m times log n over n. And for the first term, what do we get here? Well, we have worked it out, right? Bernd's result gives us a 1/squared of m, but now we look at the squared. So we get a 1/m right in here. Okay, so that gives 1/m from the approximation theory. So you see how approximation theory is very important for statistical risk bounds, and it's also very clear because if you cannot approximate it, you cannot learn it. And then there's always the question, how many parameters do you need to approximate something? And that goes basically in the variance term. Assuming that this one is finite, which comes with a lot of smoothness conditions. Okay, so now we have this bound, generalization bound for neural networks. To my knowledge, the first one in the history. What do we do with this? Well, one thing you can do is you can try now to tune, because M is a hyperparameter that you can choose as if you apply a neural network, just saying how many neurons you want to have in the hidden layer. And how do we tune it? Well, in the way such that this thing becomes small in M, right? And then you get this one becomes small if M is large. This one becomes large as M is large. And so you see it exactly the sorts of things that work against each other. and then the optimal trade-off happens at the if m is of the order square root of n over log n, square root of n over log n. And if we stick in this, then we get at the rate, we get both terms are of the same order, and the risk bound becomes bounded by square root of log n over n. And that is then a convergence rate where you can see now this convergence rate is in the sample size, right? N is the sample size. That means the more training sample you have, the smaller the generalization error will be. So it's the case with a good rate because it's not depending on the dimension. So we have put the dimension constraints basically in the CF and assume the CF to be finite, and then we get a dimension independent convergence rate for the generalization error of these shallow networks. Okay, good. Now to summarize this, and then let's go to the next topic to summarize this. Shallow network. We discussed universal approximation, then these approximation rates, and finally also these estimation risk bounds. What we learned is that universal approximation is a very weak guarantee. The proof of the universal approximation theorem is completely artificial. It's not really, I mean, it doesn't show us something which is learnable in the end. And then we discussed this thing about the shallow value networks. They are piecewise linear functions, but they behave in terms of approximation theory. They behave more like smoother approximation classes. And then finally, what I want to highlight here, because it's still misunderstood to my opinion, is that this Barron result doesn't show that you have you can somehow with neural networks avoid curse of dimensionality. It's also this Barron class is not because this, I mentioned this result by Emmanuel Candes. It's not something that only neural networks can do. Also, other methods can achieve the same rates for Barron class, right? It's just a very different way to write down smoothness, but there's nothing peculiar or nothing special about neural networks here. Now let's go to the next topic of this lecture series, talking about what additional layers can help with. And so there are four things I want to discuss. The first one is localization, then how one can more efficiently represent polynomials with deep neural networks, and talk a bit about this Kolmogorov-Arnold representation theorem, and talk also about specific properties of deep value networks. And that brings us then to these statistical guarantees, what I want to cover today. Now, localization. The question is, can you localize with a shallow network? And what does localization mean? Well, localization means that you can approximate. Universal approximation is on a compact domain, say 0, 1 to the d. But now you want to approximate in LP, but LP over the whole RD, the whole input space. Okay, and that is, although you can in the bulk you can approximate very, very well, because these networks, they are non-local, so they will always have an effect in the very far away from where they should somehow approximate something. That even if you have like you have there's a target function and an indicator function which is 0 everywhere outside, you see that the shallow network will be non-zero, still very, very far away from the support of this indicator. And that means if you then integrate this out over LP, the whole thing becomes infinite. Okay, so that means then so these things don't have the ability to localize. In one dimension, of course, you can localize. For instance, with a value, we know it's piecewise linear. So if this is the function that you want to represent, just the indicator function, say on 0, 1 or so, and then you take your value network. Of course, what you can do is you can come here, you do this, right? So you can take, I don't know, takes you 3, 4 neurons to represent this red function with a value network, and that is, it's 0 here and 0 there, so that's also converging in LP and not L infinity, but say L1, L2, L10, whatever. But this is only for dimension 1. So in dimension 2, I think there's no good result yet, but the overall idea is that actually they can't localize. What is interesting is that once you add another layer, then suddenly you get localization. And this can be, for instance, shown with this Heaviside activation function, which has goes back basically to these first attempts, which we discussed with Rosenblatt in 58. If we take Heaviside activation function, it's just the jump function from 0 to 1, and then you can represent any hypercube in d dimensions exactly by a shallow network, not a shallow network, a two hidden layer neural network with Heaviside activation function. Okay, so why is that identity true? Because so this is a sum here over this at most can be 1, this can be at most be 1, and here we subtract a minus 2d. So if all of them are 1, then this becomes a half, and the output, the second layer, will give you a 1. Okay. If one of these neurons is not activated, then we only get a number that is smaller than 2, that is smaller than or smaller or equal than 2d minus 1, which means if we subtract minus 2d, then we get a minus 1 here, and the plus 1/2 gives us at most a value that is minus a half, and then this outer activation function will make this a 0. Okay, so when do we have all of them activated? Exactly if the x lies in this hypercube. Okay, so you see this is an exact representation, and you can perfectly and that is and of course also in perfect representation in LP and so on. Now, okay, how many neurons does this? I mean, here I write it down as an algebraic formulation. How many neurons does this network construction have? Maybe good thing to everyone thinks about this for 5 seconds. So this happens in the first layers. In the first layer, it has 2D neurons. In the second hidden layer, it has 1 neuron, and then it has also 1 output neuron, right? So there's D inputs, 2D. The width is D, 2D, 1, 1. That's the construction here. Good. Now this is Heaviside network, but many things actually can approximate the Heaviside network, and so many other activation functions. And so by doing this approximation, you can then imitate the behavior of the Heaviside. For instance, for the sigmoidal activation functions, right, they're just smoothed out versions of the activation function, right? So this is the Heaviside activation function. So this Heaviside sigmoidal is this. And now if you make this alpha parameter in here larger, it means you go faster through the sigmoidal function. So that means it looks more and more like the Heaviside function. So if you make it large, get something very similar here. And many results that you see in the literature on sigmoidal activation functions, they typically have something on the speed at which the sigmoidal activation function goes here to 0 in the left tail and goes here to 1 in the right tail, because this becomes really, really important then in the end for these sorts of approximations. If you want to approximate Heaviside network, because you really have to control what is going on in the tails in the end. And for value, you can also do that, right? So this is just the construction I have shown before on the previous slide. You just do this, this, and this, and you can make the slope here steeper and steeper by making the alpha in here larger. So you need two values to represent the screen function, and the slope you can make it arbitrarily large by choosing alpha large. Okay, so that is on the localization. Now another thing you can do with adding layers is you can have better representations or approximations of higher order polynomials, and here I showed for the monomial x to the 2 to the k. Suppose we want to learn that. So input is x, a univariate function, like, and the output should be of the network should be close to x to the 2 to the k. The construction that underlies the universal approximation theorem, right? Back then we discussed how shallow networks can approximate monomials. And in this case, we have seen by using finite order differences and approximations of that, we have seen a construction that takes as many neurons plus 1 of the as the degree of the monomial that we want, right? So I discussed x squared as an explicit example, and that takes 3 neurons in the hidden layer. If you want to do that with x to the 2 to the k, you need 2 to the k plus 1 units in the hidden layer. So it's a very, very wide network if the degree is large. But what you also can do is you can just, and that's why I have picked x to the 2 to the k. In this case, you can build a network. If you have depth, you can build one network that does x squared for you. That just takes the 3 hidden units. And then the input becomes, the output of the first layer becomes the input of the next one. So then if you stick in x squared and apply the same network again, you get x to the 4, and then you get x to 8, x to the 16, until you reach x to the 2 to the k. And for that, you need then to repeat that k times. And that is much, much more efficient, because instead of here you need 2 to the k neurons, here you need 3 neurons, and you have to stack basically k layers on top of each other. So it's 3 times k. That's basically the number of parameters. And 3 times k is for large k much, much smaller than 2 to the k. So you see a huge gain in the number of neurons, and also the number of parameters that you need to represent the same function by just iterating this thing, right? So this is we also discussed here, if things have like a fractal property, like a simple thing that you iterate over and over again, then these deep neural networks can be very helpful, because you just stack that on top of each other and can represent it in a better way. So here's the representation of this as a graph. So this was the construction we had before, how to get from x to a network that outputs something close to x squared. And this depends on like how you choose the h, right? If we make this h small, I hope you can see it in the back row. If you make h small, somehow the approximation gets better. Now we use this as the input and take exactly the same network as here. But since the input is x squared, it gives us x squared squared x to the 4, and so on until after k steps we reach x to the 2 to the k as an approximate output. Now the thing is, this is not yet a value network or not a neural network, because here in this layer we just put an output and take it as a new input, but there's no activation function here. So that means here we have a linear transform, here we have a linear transform, and the composition of 2 linear transforms is still a linear transform. So we can merge these 2 things into one layer, and this is exactly displayed here. So this is now the thing where you just merge these 2 things together, such that you now really in every layer get these activation functions. And then here this was some 2k layer construction, and then but there are only k layers with activation functions. If we collapse that into that, so we get a k layer representation. Yeah.
Is it clear that for the shallow you need at least 2 to the k plus 1, and there is no more efficient way of having it with much less than that?
This is I can't give you a counter example, but I mean, I don't think it's probably known. But it's more like no one has ever found a better construction. Yeah, I would have to think about this more carefully. Maybe there's something one can say actually about this. The number of parameters you need. I'm not sure. I would have to think about it. Yeah. For now, I mean, this is the standard ways to do it for shallow networks. Now let's come to the next point, is this Kolmogorov-Arnold representation theorem. So how does that link to neural networks? And if you look at it, first of all, Kolmogorov proved it in the 50s, and that, I mean, back then there were like no neural networks, no deep neural networks, and so that he just proved it for actually disproving, I think, Hilbert's 13th problem. And so what he showed is a very strange thing, namely that any continuous function on the 1D to R actually can be represented by a composition of univariate functions. And that seems like first time when I saw this, I believe this must have been a mistake, because think about in how many ways you can write a multivariate function, how these x's that you have, how they can interact with each other. So how should you be able to write something like as complex as an arbitrary continuous multivariate function as a composition of univariate functions, which is much simpler, of course, and doesn't have the way really to model these interactions that can happen between the different variables. But it's true. I mean, that's just the way. And so, of course, very different than we typically used to think about function representation, where we think about spline bases or wavelets or smoothing techniques or kernels or whatever. So before I come to neural networks, this is by now, I mean, there's a line of work and people have cleaned it a bit up. So it's this is a much cleaner version, which I took from a PhD thesis from 2009. And the interesting thing is, it's not only that you can represent it in this form. The thing is that all this interior bit in here does not depend on the function you want to represent. So it's quite independent, or it's completely independent of it. And the only thing is that decodes information about this f it's all in the outer function g, which is also a univariate function. And here you can take numbers, right? You can pick them before you even represent the function. BP, Q, so Q is this index here, the A, and these CQs, which are indexed in this. And also this function psi that you can take to be continuous and monotone. It does not depend on the f, so it's just something universal that you can put here. So why does it now link to neural networks? It's because in terms of structure, it looks like a neural network that has two hidden layers. Okay? So if I write out what a neural network with two hidden layers is, then we can write it in this form, right? So this was basically a Celler network, and then we get another activation function in the next hidden layer, and we have the sum in the outer layer. We just do a linear combination of these activations of the last hidden layer, and the last hidden layer also has some biases DL in here. So this is just an algebraic representation of the functions with two hidden layers, where the second hidden layer has just one activation function, and the first hidden layer has no, sorry, this is wrong. So the second one has M2 activation functions, and the first hidden layer has M1 activations or M1 neurons. Now, if we compare that to this more modern versions of Kolmogorov-Arnold representation theorem, then you see some similarity. And this is generic, but it's universal. So we can take this as the activation function in the first hidden layer. There's no problem with this. Those are just numbers. We can stick them in. We wouldn't even have to learn them because they're given. But the thing is that the outer activation function here is depending on the f, because it contains all the information about the f. And here the outer activation function is something like value or so. So you don't want to put an activation function that itself is something that, or at least it's the traditional view, that should not be learnable or so. Okay, yeah, I mentioned also this pre-training thing. So in the early days of deep learning, it was to do transfer learning tasks, or you just have a small data set. You can use an existing trained network and then just chop off the last hidden layer and just train the weights in the last hidden layer. Because the idea is that the features that these neural networks learn, and that's everything up to the last hidden layer, this is typically quite generic, and only like what really matters is basically what happens in the output layer. And that has a bit of similar flavor, because the interior really doesn't matter here. So it's something very generic, does not depend even on the function you want to learn. And what's important basically is what happens really much at the output. So it has a similar flavor. But is it now relevant for neural networks, yes or no? And there were papers, like this is a paper from people also here in I think that Tommaso, he was also in somewhere in northern Italy, I think in Genoa, I believe. they said, well, in the 80s, they have this paper, this is irrelevant because of this thing that you cannot match these auto activation to this G. But then there's also a paper which says, well, this is relevant. And so this has been a bit open. And I have been also looking into this. And so what is in Vera's paper? So what she did is she could find a way such that one, if we impose smoothness on the F, okay, so you can order smoothness beta. The question is like, how does that relate to regularity of this function G? Because if the G is much, much rougher than the F, then the whole thing becomes here much harder to approximate, right? We always have the thing beta over D in the exponent of the rate of the approximation error. And if the beta over D somehow gets worse through this representation, then this is a useless thing to do. And so what she could do is she could say, okay, suppose we have a beta on the function, then we need m plus m to the power 4 plus d parameters to get our m to the minus beta. Is that now good? No, because the problem is that you need then, if I write this, right, this is the number of parameters. And so what do you get as a rate? You get as the rate n to the minus beta over 4 plus d to get approximation error epsilon. Okay, so this is then the m to the minus beta. Okay. So this is not beta over d. It's just this additional 4 in here. Okay, so there's a bit of a suboptimality in here. Now, what I want to show you is this a small thing where you can see what is underlying this Ka representation theorem. And for that, I will just give up completely on continuity, which is one of the main technical obstacles, and that makes it so much easier. So we just say, okay, we want to just represent any function, any monotone function, any function f. And the claim is there exists a monotone function psi, which does not depend on f. And for any f, we can find a univariate function g such that this representation holds, right? It has still the same flavor. On the right-hand side, we only have univariate functions. On the left-hand side, we have multivariate functions. Now, so how does it work? Here's this idea for d equals 2. So for d equals 2, we can write, we have two inputs, x1, x2. I mean, for d equals 1, it's trivial, so it's univariate. But for d equals 2, it's the smallest non-trivial case. So we have two inputs, x1, xt, and we write x1 and x2 now in their binary representation. So there are numbers between 0 and 1. So we can write this in the binary representation as the digits are a1, a2, a3, and they're either 0 or 1, right? So that's the representation, and it's not unique for rational numbers and so on. Doesn't matter, so you can fix that. So x2, we do the same thing. We call the digits, the binary digits b1, b2, b3. Now, what we can do is, for the moment, we just define a new function psi, and we define the function psi in a way that we just first take the first binary digits of x1, then the first binary digits of x2, then the second binary digits of x1, the second of x2, and so on and so on. So we just put them next to each other. And the thing is now that you can write this as a function like this. Okay, so this is now this interior bit, namely, what is the psi? The psi just maps psi of x1 will be a1 dot 0, a2 0, a3 0, and so on, right? Such that now this, if I multiply with 2 to the minus 1, this will just shift all these things by 1. If I multiply with 2 to the minus 2, this shifts by 2 positions, but those are these empty positions, and then you can fill in the second variable here, right? Clear? Okay, good. So that means we have this psi can be written as an additive function of, right? So that's the thing. Now, all what we do is the following. We write, suppose we can write. It's not so clear how this is defined. So this is a function that takes two variables and maps that into one variable in 0, 1. And so we think about maybe there's an inverse that does it the other way around, call it psi minus 1. And then we write our f, we write it, we compose it psi minus 1 and psi, so that should give us somehow something like the identity. And we call this one is now a univariate function because this maps to the numbers. So the inverse maps from numbers to R2, but in the f maps from R2 to R. So the whole thing to composition maps from R to R. So this is a univariate function. So here you see where the signal f goes into the G. And then we have the interior bit, which we can write in this form. And if we define this to be the G, then we have this representation, which is exactly like this thing. Yeah, and that's then there you see basically what the underlying argument is. The thing is that actually what this psi minus 1 does, it's a space filling curve. It's not one, it's a very specific one. It's called the Morton order. And the Morton order, right? So this is the thing. Here we define psi, but there's this psi minus 1, which is here. And that goes from the numbers from 0, 1 to 0, 1 squared, right? So, and so what does it mean? Somehow for every, it's a curve that goes to, that completely fills 0, 1 squared. That's another way to say it, a map from 0, 1 to 0, 1 squared, which is surjective. Of course, there's no way to plot it, so we can only plot it like this, like discretizations of it. And what you now see is an issue, because we want, if f has some smoothness properties, we want that G inherits these smoothness properties to as much as possible. But suppose f is a very smooth thing, then this G has this huge jumps. For instance, I mean, here's just a discretization, but it always jumps from this point to that point. Okay. So this is the psi inverse. Sorry, this is the psi inverse jumps from this point to that point. And then we compose this in the G with the f. So that means for two very close time points, we get first the function value here, then we get the function value here, which is very different, right? I mean, there's no way that these function values are typically the same. And more and more of these jumps everywhere, there are smaller ones, but they're everywhere, right? So that means if we define it in this way, then if the outer function, the function that we want to represent is smooth, this G function can still be rough, can still be a very, very rough function, which is a problem if we want to use it for something like neural networks or so. Okay, so what was then the idea that I followed is to say, okay, let's define this thing on the Cantor set instead, because the Cantor set corresponds to exactly these jumps that are occurring in the Morton order. Okay. And so what we do instead, before we would just take these binary digits and put them next to each other. Now we do another thing. We take these binary digits, we multiply them by 2, which means you can only get 0 or 2 because for 0 and 1 and then 0 or 2. And then we think about this number that occurs by putting them next to each other as in the triadic expansion. Okay, so that gives us an element in the Cantor set, because the Cantor set is exactly the set of all the numbers that you can write down in with the triadic expansion, only taking the digits 0 and 2 and not 1. Okay, so we have now defined a thing that is maps to the Cantor set, and that exactly aligns with these jumps that this thing has. Now everything works well, and so this is the map that you have then in the interior function, and you can show, okay, now you get a 3 to the minus p because that is exactly what shifts these digits by 1. And this is the result, which shows that you get exactly the right property transferring the smoothness from the outer to the inner function g. So suppose the outer function has smoothness beta, in the sense like this, and beta has to be smaller or equal 1, so it's like Hölder smoothness. And now what one can show then is that this interior function in the Ka type representation theorem has now smoothness beta log 2 over d log 3. And that's exactly the right thing, because why? we always want that beta over d, if we change the d to some d star, then this will also change our beta star to beta to beta star. But the ratios, they have to be the same, because this is exactly what defines the approximation rates, right? If we have before a 100-dimensional space and we somehow compress it into a 1-dimensional thing, what we do, that will also change the smoothness, of course. It makes it worse, but in such a way that these ratios are the same, because the approximation rate is n to the minus beta over d. So if we change d, then we have to change it in such a way that the ratio still remains the same. Okay, and now if we work it out, if we now take this, so the what's the smoothness? This is the beta star. Okay, so this is now after the transformation, is our beta star. And what is our d star in this case? Well, it's the dimension of the Hausdorff set, of the Cantor set, the Hausdorff dimension of the Cantor set, log 2 over log 3. Then if we then work out what is beta star over d star, then we set in this, and we divide by this, so these things cancel out, and it just becomes beta over d, right? So it's just the same thing. So this means this is exactly somehow the optimal thing you can hope for in terms of transferring smoothness. So it makes the object rougher, but that has to be, because otherwise you get a contradiction. You would get better approximations than the optimal approximations also. Okay, so now you can use this basically to do network approximations. And then the thing is the interior function that has, if you like recall, right? So we take the binary representation and put all these bits next to each other. So you somehow have to truncate this if you want to do that with a neural network. And so if you introduce some truncation k here, then you don't get a perfect representation anymore. Perfect representations are a bit useless, right? So for neural networks, it's all about approximating stuff. And then from perfect representations, you get an approximation bound that is of this order. And this is also, you can believe me, so it's also very fast in the k, and so it's a good bound. Okay, and now this interior function, that looks like something you can do with one hidden layer or so. But my argument is actually to learn this interior function, you'd better take, if you have the k here, you take k hidden layers to do that, because there's many techniques in neural networks with depth that's when every layer you can extract the next bit of your number. Also, if you maybe have seen these bounds on VC dimensions, the lower bounds. So it's also all these bit extraction techniques that pop up in many different places, theory of deep learning. And this always works the same way, that with every additional layer, you can extract the next bit of your number, and then you can put these bits in a new way together in later layers. So that means if you're interested in the first k bits, then you should take k layers to approximate it or represent it.
Sorry, I understand.
Yeah.
You're talking about learning this pi. Isn't this given like a given function?
Yeah. So now you want to represent that it's a given function, but it's not you could say, okay, let me take this to be my activation function. But now what we want to do is we want to rewrite this into a value network or a Heaviside network, also with the common activation functions. And then you have with these existing activation functions, somehow you have to represent this activation function. And you should not try to do that with a shallow network, but with a deep network. That's the claim. If you're happy, I mean, if you want to, you could in principle say, okay, I take this as my interior activation, it's done. But if you want now to say something about how you, for instance, want to set up initializations of value networks, and you want to use this result, then you have somehow to transfer it into a value network. Okay, and this is the architecture, how we do it. Maybe not so important to work out all these details. And this is then how it looks like. Okay, so we give x1, and based on that we get some, which only, you can basically have a tower here which doesn't have any connections to anything else. first computing you in k layers these numbers, and then you put them together. That gives you this phi function in here. And this is not a real layer because you can collapse it again into one layer. And then you have this very, very wide last hidden layer where you learn this function g. The g is rough, but you can do that with one hidden layer, but just because it's univariate, you just do piecewise constant, piecewise linear approximation. That's good enough to give you the optimal rates in this case. And then if you put everything together, then you get an approximation, because here's g tilde. This is just a piecewise linear approximation of the g, so that gives g tilde, and that gives you something that looks close to what comes out of this Ka representation theorem. In the sense that the thing is close to the function you want to learn. And it's a value network in this case. Okay, so we have now transferred everything into values. There's nothing and like non-common anymore. And based on this Ka representation, yeah, that's the story. Now, I published this, I think, in 2021, and then, you know, like it's a very nerdy stuff. Cantor said blah blah and so on. So we get every year your 10 citations or so on this. No one really cares. But now that last year in April, not yet a year ago, there was this paper, and I just checked it. So this is from April 30, 2024. And so as of today, it has already, maybe it has by now with 1,005 citations, so that really goes by the hour. That had a huge impact. And so what they do is, based on this previous theory that we developed, really came up with something that is apparently practical. Otherwise, it would not have such a huge impact. That I mean, even in machine learning terms, if you're in the first year, not even a full year yet, can generate 1,000 citations, that means it's considered to be some form of breakthrough. And they really used this idea of Kolmogorov-Arnold networks to come up with something that is feasible. And I want just to show you how what their architecture is. It's a bit different what we have done before. So what their take is from this literature is to say, okay, so here they compare. This is I copied that from their paper. So they compare the deep feed-forward networks, also called multi-layer perceptrons, based on this idea of perceptron, with their Kolmogorov-Arnold network structure. So here they say, okay, so a cellular network can be written in this form. We know this. Now these Kolmogorov-Arnold representation theorem, this has this form. So what shall we do? What we should do is we should make these activation functions learnable themselves. Okay, so they are something. I mean, here in principle, this interior one is given, but they also say, okay, even that one can be learned, and the outer one is G or F dependent, target function dependent. So let's have this be learned. And whereas Kolmogorov-Arnold representation is on 2 layers, just make it as deep as you want. Maybe have 3 layers or so, right? So everyone has done these layers, and in between we see these summations, and then they also put these summations in there as another thing. Okay, so that's the idea. But now, how do we learn activation functions, right? So we're used to activation functions are given to us. How do we learn them? So what they imagine is that somehow, and I think this is very crucial for the success of the whole thing, is that you have as a default, you think about it should be value. Okay, so like you should put a lot of prior weight on the fact that these activation functions are value, and only if the value is very, very unsuitable, then you want somehow another part to take over and kick in. And this is in here. So instead of value, they take CILU. CILU is this thing, and here's CILU plotted. It's a smooth version of the value. You see, it's a very similar thing. It's also sometimes called the Swiss activation function. So they put the value here. They put a weight here, which can be learned. And then they have a second part in their activation function. So this.
So it's value, but without parameters inside there. Okay, forget it.
Yeah. So this is on top of all the other parameters. Yeah. So the activation functions themselves are now parameterized, right? And so this has one parameter, how much you weight the zero part, but this gets a large initialization. And then you have this other part here, when you do a spline basis expansion. And this has two parameters here, which are typically initialized by small values. Now you can wonder, so this W tilde is redundant because we have parameters in here. So why should we put another parameter in here? But this we will come to this. There are good reasons by now why you want to do these sorts of things. Although, like in terms of representation, that doesn't make any sense. But it's you have to think about the learning aspect that underlies them. Okay, so we have these sums over these spline functions, and there are lots of problems involved with this because spline functions, you probably have seen them. They look like this, and the next one looks like this, and so on, right? These B-spline bases, but they have support. And now it could happen, for instance, that somehow the input into the activation function falls outside of the support of your spline functions. Then you have somehow to append the spline functions with more spline functions and so on. And they discuss all these things, and they probably have thought about this for a while, how to do it in a smart way. So just overall, this BI, they are given there, these basis functions and the CI and the W tilde will be learned. They will be initialized by small values because you want basically to take the CLU over if that is a good choice in the beginning. Okay, so that's how they do this. Another thing that comes out of there, I'm not so sure how I should evaluate this, but one thing they say they can do with KNNs, which is hard, is with artificial neural networks if you want to learn, say, formulas from your network. Okay, so here they think about so they want to learn that the input to the output map is given by this formula. And so they have a way, they find a way how they can somehow learn this algebraic formula, not only weights, right? So it's something which is interpretable in the end from the networks. And so they also do sparsification and well, I mean, they take out some connections, and then they have a set of elementary functions that they're allowed to fit, and they do that in these activation functions, and based on that, then they come to these formulas. So if you think about, I want something more interpretable, or I want to find Newton's law with neural networks, so how to do it, then this is maybe one way to get there. If you have to specify a number of elementary functions that you're allowed to, that can occur in these formulas, and based on that, they try to fit one that matches. But the fit can be very, very nonlinear here, right? So you see something e to the y squared plus sine pi x, which is their formula in there. Okay, so just to wrap up, the key thing in these KNNs is that you have these learnable activation functions. They need much less parameters. If you also read these blog posts about them, people who played around with them, they say they fit everything, and this may be also their problem. So you get very, very good fits with these KNNs, which is a problem with deep neural networks. They typically are not very parameter efficient. They just take too many parameters. We know this with these overfitting, and so that's something that shouldn't actually happen. And they somehow are much better in that respect. The question is that now more interpretable than other methods? So they make a point in their paper that's hard for me to judge. If I look at this, suppose I would not know about Kolmogorov-Allman networks, so I think probably one would say what they propose in the end is a way to make a spline fitting, which is a key technique in approximation theory, to make that deep, right? So you can make everything, all methods that we have in the world, you can make them deep. And that's maybe also a good thing to consider. People now talk about making kernel regression deep and making this and that deep. And I think in the end, what really under the, comes out of here is just some a deep spline fitting method. But the important part is maybe that the way they were inspired to come up with something which is very different than traditional network architectures, really because of the existing theory. If you read the paper, you really see that back in the way they reason and they propose things and so on. You also saw it in their plot. that they start with this Kolmogorov-Arnold networks. That's also a Kolmogorov-Arnold representation. That's also how they name their network structures. And so I think this is a very positive example how theory can contribute to practice, right? So what we should maybe more do in practice, in the development theory, we should go more to these things where we don't understand so well what is going on, all these phenomena that are still around that are not very well explained. Try to derive some theory, maybe are very far away from that, but that might be able to be picked up by others then to come up with new ideas. And so, because otherwise the main criticism of theory is that we always run behind what happens in practice, and this is just the opposite, right? So here was first the theory, people writing papers about Kolmogorov-Arnold representation being irrelevant or relevant and so on. And then based on that, practitioners really can digest all this and out of this come up with good methods. And I believe this might be a way forward to come up with meaningful, impactful theory. Okay, so that's this part. Are there questions about this?
Does anybody use them? Yeah. Or
Yeah, I believe so. Yeah. So otherwise, you don't get 1,000 citations.
use not the site. For real
Well,
real problem.
I
Engineers.
I mean, I'm not. No one read all these 1,000 papers, not including me. I feel that there's a lot of enthusiasm about that, and they try. I mean, they came up with all sorts of variations of that. But I'm not able to give you now this say, okay, for this specific example, it has been state of the art or it won a competition or so. But I think the way they, I guess there's this very serious stuff. And they have a lot of examples in their paper where they show how well it works. And I believe they have done that quite seriously, and it's impressive. Otherwise, people would not have picked up this, right? I mean, everyone in their paper has somehow that they can beat all other methods on MNIST or so, right? But I believe this is really on a more profound level. Let's continue then. So I want to briefly talk about value activation function has very specific properties as well. Again, independent of the depth, is always piecewise linear in the inputs. And so one natural thing is then, for instance, to count the number of pieces that it has given a number of parameters. And normally, like approximation schemes, then the number of parameters is basically the number of pieces or of the same order. But here that can also be like much larger. And also then I want to briefly talk about value networks where you just take small parameters, which is a big thing in the universal approximation property. You know, you have to take some parameters to infinity, which generates all sorts of instability. And that's one very specific thing about approximation theory for values, that you can always stay with bounded parameters. So one thing which is important is that these values, they can represent identity in a very simple way. And because they're just projections, and then if you apply projections twice, so you get this. And that is important because we know that sometimes information has to be transferred to later layers. Think, for instance, about these Heaviside networks, where you have the Heaviside activation function, and after one layer, that will map into the values 0 and 1. And you can only transfer then the bits, individual bits later here, but here with the value, you can transfer things into later layers for just the full numbers, and that has a huge advantage. Think about also many of these constructions, they are like, okay, we do construct different things at the same time, but some of them are more complex than others. So maybe one thing needs 5 layers, the other one needs 7 layers. But then we need to somehow synchronize that we have both these outputs at the same layer, so we can just with these values, very simple in the approximation theory, just do the identity and then move that to the 7th layer, which with sigmoidal activation function, right? You destroy these values by mapping them to 0, 1 afterwards, and that's an important property. Also, maybe this one I skipped for time reasons, so we will see later examples where you can, with a few parameters, you can generate extremely highly oscillating functions with deep value networks, and the depth increases this discrepancy between number of parameters and number of pieces. Here's one thing, if you're bored by my talk, you can solve a conjecture, and this is the maximum function, is also piecewise linear. Maximum of, say, you get 2 to the k inputs, and you want to compute the maximum of 0 in these 2 to the k inputs. Then it's quite easy to show that you can do that with k+1 hidden layers. So sometimes if people come for an interview to Twente, and then I give them this as a problem, because it has different parts, right? You can see, for instance, you can reduce from induction step from 2 to the k to 2 to the k+1 or so, because you can split it up in 2 to the k pairs of each 2 each, and so on. And there are different other ways you can maybe solve this thing for k=1 and different things, and then you have to combine it. And you can see like how students can somehow split this problem into smaller problems, see how many of these smaller problems they can solve. So this can be perfectly represented, and it's an important function as well. Which also in my work we have used it for certain feature learning problems and so on. So to have the ability that value networks can do the maximum. The conjecture now is that k hidden layers are not enough to represent that function exactly. And this is obvious for k=1, because for k=1, you have the function. How does this maximum look like? It looks like this. So those are 3 linear pieces, right? You have inputs x1, x2, and you can put here the x1, here the x2, and those are the 3 pieces. But with the shallow network, you always have to have full hyperplanes, and that means somehow the decision boundaries, they have to stretch over the whole thing. So something like this, like a Mercedes star, so you cannot generate with a shallow network. That's clear. So for k=1, it's obvious that you cannot do that. That you need at least 2 hidden layers for that. But once you go to k=2, there's no proof that 2 hidden layers is not enough for just x1 to x4, right? If k=2, we have 4 inputs to compute the maximum that you can do that represented with a 2 hidden layer neural network, where you can take any finite size of for the width, whereas it's then easy to show that with 3 hidden layers it is possible. So there are some things, and for in the case k=2, there's a paper where people use it's a newspaper where they use tropical geometry for trying to prove that, and then they rely on an assumption or other conjecture that I believe is as hard as the thing they want to prove in the end. But so there are many other tools you can in principle use as from other areas of mathematics, like maybe tropical geometry has a lot to do with piecewise linear functions, and that you can then apply to these things. Okay, here comes now an example of a highly oscillating function can build with a few parameters by stacking value layers on top of each other. How does that function? Yes. Yeah, not infinite width, but any finite width. Yeah, infinite width. Well, it's on the whole RD. So then R to the 2 to the k. I don't know whether infinite width would help you, but I think people will want to do that for finite width.
Just 1 or 2 slides.
Yep. Mm-hmm. This one or?
Yes, okay.
Yeah, so here we have, I mean, the idea is like, how can you generate with few parameters more linear pieces? So this is a bit the idea here. Like with 1 hidden layer, you generate piecewise linear functions. And so what you can do with the second one, if you take, for instance, just the identity and just apply value once more, you can do that, right? You put parameter 1, and then apply value, and say this is. Okay, now I first take another color. Say this is the thing, the coordinate system. So then what you get is you get afterwards this function, right? Because the negative values are set to 0. And that has suddenly, like with one parameter extra, you get basically 3 more pieces which have a certain structure because they all lie along the same hyperplane. So this is one way to see how you with adding layers, how you can increase the number of linear pieces, of course, in a certain structured way. And then the question is like whether the structural constraints that are implied by the imposing layers on each other, whether that can help you to approximate interesting functions. And you have a question about? Okay, good. Now here comes the example. And this is this function over here, this t function. So how does it look like? We're just interested of this, how this t function looks on 0, 1. So, okay, here's also 1. So we have here it's 0, and then we go up at a half, it's at 1, right? It's 2x. And then we subtract the second value kicks in, and it pulls that down here. So that's how this function p of x looks like. So now, how many neurons? This is the representation as a shallow value network with 2 neurons. Now we are allowed to do deep network, so we can compose that with each other, right? And then build a deep network based on that. And what is going to happen now with this construction? So what happens if you apply t to itself? So who knows? That's also sort of. So what is t composed with t? What is that? Which function do we get? You're just interested on 0, 1. Fun. Perfect. Yeah, 2 triangles. Yeah, that's how you. So you get to see. The H-base is on piecewise constant. It's more like these Faber-Schauder systems and so functions. Yeah. But the thing is they're not localized, right? They're always functions on 0, 1, and all these function systems, they will take these things individually as functions and make them on. But here you have them really as a global function with 2 peaks. That's the difference. Okay, so this will be the thing, because on 0, 1, you go with the first function, you map that to 0, 1, and then you apply on that part, you apply on the output of that one, you apply the t function, and the t function on 0, 1 gives you just 1 bump, right? And the other way around here. So from here, you go from 1 to 0, and if we go backwards, that gives us another jump, which is the other way around, but because it's symmetric, it looks also exactly the same. Good. And if you do that now k times, you can imagine what happens is we get 2 to the k of these sawtooth functions next to each other. And we have just taken very, very few parameters to do that, right? Because it's in every of these constructions. I mean, there's one parameter, the bias is 0. Here are 2 parameters, and there's a 1, and there's another one in here. Okay, that's the construction of this tk, which means just composing k times the t. I'm not sure whether you can see it from the back, but it's the same story as before. Here, this is one of these t things, which are shallow networks, and then we have this thing that we stick in the t as the input of the same construction in the next block. And these things don't have activation functions, so these 2 things collapse. And then if we write it down as a deep neural network, we get this. And here I put all these parameters so you can see all these things. So you see that in every layer we have 2 neurons in this construction, and it goes over k layers. Yeah, we get this t to the k, which has how many pieces? 2 to the k plus 1 or 2 to the k, I don't know. Something of the order 2 to the k. And it has of the order of k parameters, right? Because 2 layers, so there are 4 parameters here, 2 biases, so 6 parameters per layer, and this times k, so 6 times k, and then maybe here another 2 or so. Okay, so we have found a way to represent a function with an exponential number of pieces exponential in the number of parameters, right? 2 to the k, and the number of pieces is of the order k. And that's quite interesting. But the question is that useful for something? And it is useful for one thing to do this. And it's useful if we think about, again, this multiplication problem. How can neural networks, how can they multiply things? And I said this is not very obvious because it's a bit orthogonal to the structure imposed on how these neural networks look like. And one way you can see what has to be done for multiplication by polarization identity, if you have a deep network, it's enough to know how to build a network that can square, right? It takes an input and squares that, because in the first layer, you can compute, if you have x and y, you can compute this thing. And then in the second layer, you just stack that in and you have your network that computes x squared based on that thing, and that just gives them another layer. So just squaring a network that is approximately the square will allow you to implement this one approximately, and that gives you an approximation of the multiplication operator. And this now has a surprising answer for value networks. First, let me go back to the lecture 1. So you see, I took that from a different set of lecture series. So this lecture 1, on Monday we discussed how we did a generic way to approximate x squared with the second order differences, right? So we have that on the board. And then with that goes and so here one of these issues is that the parameters in the outer layer, they become arbitrarily large because you have to make h tend to 0, and this 1/8 squared will become large then. And for value networks, we can now use a different way to construct it, where we don't run into these problems of arbitrarily large parameters, and that is in this one here. Okay. So this is the TK. TK is basically what was T before. I just put in another parameter here. Why do we do this? Because the way the T is defined, here this construction also has, for instance, in this layer a parameter 4, which we could pull out and make a 2 here and a 2 here if we want. But still then we have parameters 2. And to get the parameter values down to 1, we have to be a bit more somehow optimize a bit more. And therefore we don't have T's, but we have TKs instead. So if you look into the TK, you can see that these things, all these parameters that occur here in the Shallow network representation, they are smaller equal 1. So here's a 1, here's a half, here's a 1, and here's also something that's smaller than 1, here's a 1. So the largest value is a 1, which is more natural than, say, 2. And because of all these explosions that can happen with depth. And now we define RK to be the composition. Before it was T composed with T and so on. And now we compose a T1 with TK in this way. And the thing now is that this RK here, this has a very good approximation of the half circle. Okay, so if we sum these RKs from 1 to m, then we get an approximation error for the half circle, x times 1 minus x, that is of the order 2 to the minus m. Okay, so m is the depth basically that we need to carry out this construction. And so that means that in all of them, all of those ones we can represent with a deep neural network, which doesn't have which has a fixed width, and it takes m hidden layers, and we get approximation error 2 to the minus m. Okay, so it's a very good approximation error, and this is by putting these very highly spiking functions that we have seen before, reweighting them. This is the reweighting step built into here, and adding them up. And that gives us, in the end, then a very good approximation of this half circle. Here's in a picture how that looks like. So those are these. This is T0 or T1. How did I define it? I think this is T1 here. This is the T1. This is the T2 function. The T3. No. This is R1. just read what is written here. This is R1, this is R2, and this is R3. And here those are these functions. If we now add them together, then we get, if we just add the red one, we get, well, just the red one is this one. And then if we add the orange one on top of this, then we get this one. And so you see this half circle line, so it's a bit stretched out here. This is x times 1 minus x. We get very, very fast approximations of that function with these very fractal shaped looking functions over there, but they are down weighted, so that works. And we get, it's much more efficient. And here we also have a lower bound. Good that you're still here. So here we do have a lower bound for how many neurons a shallow value network would need to do the same task. First of all, this construction, again, it takes m hidden layers, as we said before. It has, because it has fixed width, so the number of network parameters is still of the order of m. All the parameters are bounded by 1, so we don't have to think that parameters can go to infinity or have to go to infinity, and we get an approximation error of 2 to the minus m. For shallow networks, and because shallow networks in one dimension, they are equivalent to piecewise linear functions, and we have lower bounds for approximation by piecewise linear functions. That has to do with this saturation that I also explained before. We know that for this function, we need at least 2 to the m over 2 parameters to achieve the same approximation rate. Okay, so now you see that there's a huge gain for large m, at least there's a huge gain between the number of parameters. But this construction, the deconstruction, requires compared to the minimal number, and that's also the required number. So that's really the order that is required for a shallow network. They're really linear versus exponential. Okay, so that's another construction where you see that depth can be beneficial. And it's really, I mean, we discussed it also this morning, that value networks using this sort of fractal properties of composing functions with each other, that is, with a few layers, you get to very, very complex objects. And some of them are indeed useful for function approximation. Now, if you can do the half circle, you basically can do x squared, right? So you just subtract this linear thing here, and you have x squared. You have x squared we solved before by polarization. You can have very good approximations of the multiplication operator. There's the big question: is that now learnable? Such a construction, it's just approximation theory. That's a bit hard to answer. So people tried it in different settings. It's probably a bit less efficient in practice if you want to learn it than what the approximation theory shows you. Okay, so now based on this, what I said before, you can now come up with a network that has m plus 4 hidden layers. It has, this is the architecture, the width vector. Like this is 2 inputs, x and y, 1 output, which is approximately xy. In every hidden layer, it has 6 units, such that with this previous construction, polarization, and on top of this x squared thing, right, the x squared always requires a 3, but we have to do that twice because it's in here. So we have to do, that's one of these inefficiencies, right? So there's certain things like squaring, but if you need to do that twice, you also have to implement it twice in your network and in parallel. So that means each of them needs 3 hidden units, and we need to do that twice. So we have 6 hidden units for the squaring. And then we get the same approximation error that we have seen on the previous slide, the 2 to the minus. We burn some additional hidden layer because we first in that one layer, we have to compute these sums and these averages. And there's a problem because that's one thing also where a lot of mistakes happen. Here it looks like, okay, in the first hidden layer, we just compute the difference and divide by 2. But you always have to keep in mind, you also have to take the value afterwards before you can pass it to the next layer. And so that can destroy things if they are negative or so. And so one has to be a bit careful with all these things. Okay, so this is the construction, how that looks like from the paper, from my paper, how to implement it. This is one thing. Okay, so once you can do multiplication, you can do a very good network approximations of monomials. Then if you have monomials, you have polynomials and so on. But for good function approximation, you also want some form of localization, which is important because somehow you localize, and on each of these local bits, you you do a local Taylor approximation also, right? So you have two things. You have a partition of unity, you build your polynomials, and then you somehow, once you have done that, you take on each of these pieces of your partition of unity, you take a Taylor polynomial that just corresponds to the Taylor polynomial around some centering point of this function, and then you multiply them together and you sum everything up, and that gives you a good function approximation. And so how do we do localization? Well, somehow you do that via this partition of unity. So here you can see that these are these triangular functions. They look like value functions, but they also have multiplications in here. So in one dimension, you just localize by, okay, so you take functions like this. And if you add them, so now each of them is one function. This is one function, this is one function. If you add them together, right, you get on 0, 1. On the input domain, you get the 1, which gives you then the partition of unity. If you do that in several dimensions, you have to multiply these things, and the multiplication you have to implement that via them, or you approximate it via deep value network construction. This one you can do, of course, with one hidden layer, and then the multiplication we have seen that before how that works. Okay, so that gives the partition of unity, and so those are these functions that we want. I said, all right. Oh, no, sorry. Those ones are the localized functions. I should just read my slides. And this is just the proof that this actually adds up to 1. Yeah, okay. Okay, and so how to do the Taylor approximation. So once we have a centering point, A, and we know what the smoothness is of our function, so it is the function f that we want to represent has smoothness beta, then we know that all the derivatives up to beta exist. Then the Taylor approximation up to the order beta is then given by this expression, and it should approximate f up to order the difference between x and a to the power beta. And now we can just rewrite this as a polynomial, right? So this is multi-index notation, so x minus a, so x is a vector, and then we just multiply that component by, so x1 minus a1 to the alpha 1 times x2 minus a2 to the alpha 2, and so on. Okay, and this is also those are monomials. This is the L1 norm, those are monomials, those are coefficients that come from this representation. And since we know how to do monomials, so we know how to approximate that with deep value networks. And for this all, if you want to know the details, also you can see that and check out the article. And if you then put everything together, so we have localization, we have local Taylor approximations, we built that in parallel, which is make the network wider, build it in parallel, and then multiply them together and add them up. And then, right, we get to see an input. The input will look and will only activate the functions in the partition of unity that are close to this input, right, because they're localized. And then they are multiplied with the Taylor polynomials at the centering point of this localization. And in the sum that we have on the top, then only these local Taylor polynomials will show up because the localization has taken care of this. And then this Taylor approximation will behave like the function value at that point. That's the rough idea. If we stick all of this together, then we come to a function approximation result that says, okay, suppose our function is beta smooth, and here it's in the Hilbert sense, and beta can be larger than 1. And that's a standard way in non-parametric statistics on how to extend Hilbert smoothness to often people in analysis would call this SR smooth, where S is the integer part of beta and R is the fractal part of the beta. Okay, but think about just beta to be an integer if you want. Now then there exists a value network that has depth scaling with m, so you can choose m and capital M to hyperparameters here. And the depth will be basically of the order of n, and the number of units per layer will be bounded by a multiple of capital N, and the number of non-zero network parameters will be bounded by a multiple of n times m. such that we get this bound. Okay, so in this bound, you see certain things that we have discussed before. First of all, you see this rate that we like, right? This is the approximation rate. Here what I called earlier, D is called here R in this statement. So that is the dimensions, so it's beta over D, and it's n to the minus beta over D. It's not entirely what we want because the number of parameters is not n as before, so it's a bit cheating this bound. The number of parameters is capital N times small m. Okay, so here we should have, if we would have the right bound, we would have this times m. We don't have the m, which means we lose a bit if m is large. If m is large, then this would otherwise give another small number with which we multiply here. So therefore, the second term tells us basically we don't lose so much compared to the optimal approximation rate if m is not too large. M is basically the depth of the network. So here, we don't want the network to be too deep because otherwise we lose. The first part comes from these things that I discussed before, that the depth m we get for multiplication approximation error of the order 2 to the minus m, and then we have it loose. It doesn't really matter so much. We get also an n in front of that, but basically the whole thing is here the 2 to the minus m. And in this part, which comes from these approximations that I explained before, we want to make m large because then this one will be smaller than that one. And now there are two things that work against each other. So what is a good choice then is to make the m to be something a multiple of log n, right? If you make it a large multiple of log n, then this one will be of a smaller order than this one. And log n is small, right? N will be polynomial in the sample size later or so, but log n will be just another log term. So in the end, people always lose some log terms in the convergence rates if we do that. But there's also something which prevents us to go to too deep networks. And there's also for feed-forward neural networks, people observed that, I mean, also for training, and so there's some instability unless you put resonant architectures and so. Anyway, so another important thing is about this number of network parameters S here, because that causes a lot of things downstream. So what is the number of, if we have a width bounded by capital N and depth bounded by little m, what is the number of parameters of such a neural network? Who knows that? We could now that give people a small exercise. What's the number of parameters of such a neural network? Say every hidden layer has exactly width capital N, and we have m hidden layers. So how many network parameters do we have then?
It depends on the input layer.
The input layer, say the input layer is also that will also count. But think about the n to be something that later will scale with the sample size. That will be very large, and the input will be maybe 10 or 700 or so, but that will be fixed. So the input dimension will be fixed, and the asymptotics will be basically in the width in each of the hidden layers will be driven by the n. So the whole thing. I mean, you have a good point that there's also the input layer, which gives the input layer will give you d times n parameters, right? Because yeah, that's the weight matrix that is d times n, and plus the biases, which gives you another plus n in that one, right? So that's the thing. But all the other layers, they give you n times n for the weight matrix, and then another n for the biases in that one. So overall, if we have m layers, the number of parameters in the network is m times n squared. Okay, so that means if we now require this number of networks parameters to be n times m, if the n is large, and n will be very large later, then we mean that we really talking about sparse network approximations. Okay, so in these constructions before, you see a lot of things can be done in parallel. Typically, these things are very narrow, these individual bits, and lots of these cross things that are possible in a neural network, they're never activated, so they're all zero. And if you count that, so you mean in first order, these number of parameters are useless. It's really like basically every neuron has an in degree and an out degree to how many neurons in the next layer they send signal, and from how many neurons from the previous layer they receive signal that is not weighted down by 0. And the in and out degree, basically what it says should be constant for every neuron, whereas it could be in principle also n, right? Because there's n neurons from which a neuron can get signal and can send a signal to another n neuron in the next hidden layer. But if that is roughly a constant, the in and out degree, then you end up neural networks that are have this property of this sparsity property. And you see that in practice. You can look at, for a given input, which neurons are activated, and you see typically there's just a constant fraction of the, like a few neurons per layer are activated for every input. So maybe it's not a number of parameters, but there are certainly some sparsity patterns, and we can discuss that at length. But it comes out of the theory. If you work it out like this, you see somehow sparse approximations are good. So that's all what I said already. And now let's go to a statistical problem. Okay, my laptop is soon to collapse. Does someone have a charger? Then I can charge it here. An Apple charger. Okay. I have. I'm sorry. There's still 5% battery. Okay, let's talk about statistical problems now. So what's the statistical problem? We basically discuss a similar setting as what I mentioned for what Andrew Barron did in this framework. So just on a slide that is less mathematical. So we think about the learning problem, like they want to learn distinguish cats from dog images. And we have input space. Here's every image, and every image is a set of pixels. And then these pixels are values. So this is the number of pixels is the input dimension. And then we think somehow in the background is an unknown function f that sends for every meaningful image, it maps that to the corresponding true label, either cat or dog, right? So this is the thing. If we would know this function f, if we see a new image, we could just evaluate it, and then we would always get the correct label, cat or dog. With our machine learning procedure, based on data, we want to find and learn an approximate version of this function f, because if we know it is very, very well, then we can do that almost as well as if we would know the correct somehow underlying true function that can do this task. And so now, clearly, the more data we have, the easier the problem should be, right? We have more information about the underlying function f, and that should somehow give us better generalization bounds. And so what we're always interested in is how, if we increase the number of parameters, oh, thanks a lot, how that generalization error decreases in the sample size. And that means the training sample size. Okay, so that's the rough framework. Now here I just talk about someone asked me, Michael asked me about the non-parametric regression model. Here we work just with this non-parametric regression model where we say, okay, we have as training samples, we have n samples consisting of input-output pairs. Input is in RD, output is just real values. It's a real valued response. Think about, you get to see 100 covariates, and based on that, you have to predict like how long a person still will live, or these sorts of problems. On top of, so there's a function that maps the inputs to the outputs, but each output is also perturbed by some additive measurement error epsilon I, which we take for simplicity just to be standard and normal, and they are all IRD, so they're all generated independently. Now, based on this data set, the underlying function f that I had on my previous slide would be this function f, which we would like to learn based on the data, right? We don't know it. We want to extract it from the information that we get only through the data that we observe. And why do we study that? One reason is because it has been studied a lot. It's like a benchmark model for supervised learning. We know a lot of optimality properties of other methods. We know what is optimal and so on in terms of these convergence rates. And then we can try neural networks and can see how well they perform on this task. Okay, so how do we set it up? A bit of repetition of this Andrew Barron stuff before. So we, as in computer science, we pick the architecture beforehand. So that is not learned. So we pick a number of hidden layers that we think is appropriate. And then also the width vector, how many neurons in all these hidden layers. So that's the L and the P. The L is the width, P is the vector of neurons in the individual layers. And on top of this number, because we have this thing about sparsity, we also pick a sparsity index here, how many non-zero weights we expect as an upper bound. And then we can put all the functions that we can generate with this architecture and this number of non-zero parameters, where we don't know where the parameters are, they're just non-zero and somewhere in the network. And all these functions are now they generate this function class. And now we don't know, of course, how people train it in the end, right? Whether they do empirical risk minimization, which is computationally feasible, or whether they do gradient descent or ADAM or some other method, or right? So the theory that we develop is for a method that takes the data and it spits out a neural network in this class. I think this is one thing that all these methods have in common, right? Whether you do gradient descent or a stochastic gradient descent or some other variation of it yourself, you always take the training data, you fit a neural network, and in the end you get a neural network back. So the learned neural network is called f hat n. So that seems a bit vague because, for instance, you could not look at your data at all and always give you back the network with all the zeros in it. That would be really bad reconstruction, or you can really exploit the properties. So we will see that coming back in the bounds later. So this so-called optimization error that controls that in one number how well these methods do. Okay, once we have our method, once we have our learned network, we can now work out what the generalization error is. The generalization error here, I write it a bit more formally. So we get to see a new x that we haven't seen in the training data. So in test time, we get to see a new x that is generated independently of everything else, which we have seen before and which goes into the f hat n. And we are supposed to predict what is the corresponding y. So the f hat n is the prediction of the y. And then we basically compare it to what the true f is. And that tells us like how, and then we take a risk, right? We average the square distance, like what we like to do in statistics, and that bounds then the generalization error. Okay. And then we want to see like how this decreases in the sample size. Now the thing is, we can of course apply that to the standard framework, which is to say, okay, our function that we want to learn is just 10 times differentiable or so. The problem with this, actually, there are two problems with it. The first problem with this is there's curse of dimensionality in these non-parametric grades. The optimal non-parametric grade that applies to all methods, right? We have limited knowledge about our function f. If we just impose smoothness, then it's known that the optimal method that any method can achieve is n to the minus 2 beta or 2 beta plus d. D is the input dimension. If d is 100, then this rate will be always very, very small unless beta is also extremely large. And that is called also, that's another incarnation of the curse of dimensionality. And that means in high dimensions where machine learning strives and successful, this will always be a slow rate. So that cannot explain this regime where machine learning is successful. So there has to be something more than just smoothness in the target function if we want to get to faster convergence rates. The second thing is that for this standard framework, we're just imposing smoothness. Tons of other methods are also successful. So that will not allow us to work out a situation where neural networks are somehow better than existing methods, right? So then we can't say why taking neural networks, why not taking kernel smoothing or wavelets or splines? So they all achieve this optimal rate. So that's a bit a useless task then, just to prove that neural networks also can do that. It's like universal approximation properties. Tons of other schemes also have universal approximation property, right? So that doesn't really help us to identify why we should neural networks if all the methods have the same properties, right? We need to go to scenarios where neural networks are somehow unique. How do we set this up? So this is a bit the idea. If you have a simple task, then neural networks and random forest, sometimes neural networks wins, sometimes random forest wins, and so the neural networks really become successful if there's some underlying complexity in the learning problem. And one thing you can imagine, which happens a lot in these state-of-the-art applications, is that the thing that you want to learn itself has a hierarchical structure. So that is an assumption that we make on the state of the nature. It has nothing to do with the neural networks. It's just like how we believe the things are built that we want to learn at the end. And so many things there are built just like an algorithm or so, where you have little modules and you put them on top of each other, and that generates the complexity of the whole thing. So that means if the thing you want to learn itself has a sort of compositional structure, then that might be a natural function class, first of all, to model things that happen in nature. For instance, if you think about how should I model the function that maps the like how much I smoke to the risk that I get lung cancer or so. It's not just that your smoking immediately causes the lung cancer. Your smoking causes something in your lung, and this causes another thing, this causes another thing, and this and so on. And after a long chain of things, somehow the lung cancer comes or not, right? So there's a composition underlying that, and we just see the result of the composition, but we don't really maybe don't fully understand the mechanism. But there's a compositional structure and lots of other things, like you can also for object detection on images or so, that we build first edges, and then based on these edges, you combine them and you get higher order topological structure, and so that there's some sort of compositional thing. Or if you think you want to learn an algorithm or so, then you also have these things that are little things, and you just put them on top of each other. So, and whereas now a low-dimensional structure hidden in that assumption is that, like in every of these abstraction layers, you're not going to take all the objects that you have built before. I mean, here's this thing, I don't like it so much, but like if you build a word, right, you don't take all the letters in the alphabet to build a word. You just pick a few of them. You build a sentence from words, and you don't take all the words in your that you have, but you just pick a few ones, right? So it's always you pick a few of the things, and with different things you can cover all of this, but all of them take a few ones. And this is exactly this thing which is nowadays called compositional sparsity. There were some earlier articles, but this is the way I formulated it in my article in 2020, where we say, okay, so we suppose that the function that we want to learn itself is a composition of q+1 functions, which we don't want to learn, right? We don't want to identify them. They're not even identifiable. We just assume that they are there. This gives us faster rates in the end for learning the f. Okay. So how are these functions? So they can map from different, say, Euclidean spaces with different dimensions. They can be large, maybe 1 million and another 1 million. And we assume that these GIs, they are vector valued functions. They have component functions. These component functions, they all have the same smoothness, just to make it a bit easier. And the key thing now is that these component functions, each of them can only depend on TI variables, whereas we in total have DI variables. This is the sort of sparsity that is often present in these problems. And the TI can also vary, but think about TI as a small compared to the DI. And different components can pick different subsets, that all the DIs are picked, but they're in different components, and each of them has at most TI. Now, there's another thing. If we impose smoothness on these beta i's in this non-parametric regression model, what defines the hardness of the problem? We have a function that we want to learn, and we have noise. And the smoother the function, the better we can separate it from the noise. And that defines basically the hardness of the whole thing, and how much we have to smooth and so on. Now, if we impose smoothness on these GIs, then that doesn't mean this is the smoothness on the F. So we need somehow to understand how smoothness imposed on GIs in such a composition induces, what does it induce in terms of smoothness on the F in the end. And this is exactly this notion of effective smoothness. So if you have a Brownian motion has smoothness a half, basically. And then if you compose a Brownian motion with a Brownian motion, so you have iterated Brownian motion. In Italy, everyone knows stochastic processes very well. So what's the smoothness of the iterated Brownian motion? Pardon?
Gets worse.
Yeah, it gets worse, and by how much?
I thinking that this is exactly the same thing we were discussing this morning about the fact.
Exactly, yeah, that happens as well. Yeah. So if you're below 1, then somehow you multiply it. Indeed, yeah. So actually it's a half times a half. So Brownian motion is a half if you iterate it with itself, or either you take the same realization or independently generated a path, so you get a smoothness a quarter. It's a half times a half. So or almost. I mean, it's not exact, but and this is exactly what happens here. So if you're below, if you impose smoothness beta I on GI, and those are the smoothness indices that came later in the composition, if they are below 1, then you have to multiply that. Otherwise, it just stays the same, right? That can deteriorate the smoothness if further down in your composition you have low smoothness functions. Okay, so that means function GI somehow induces functions beta I star in the F. Okay, each of them induces a beta I star. Now, which one to pick? In the end, what you have to remember from this compositional sparse function class is just these Ti beta I star that they will determine everything later on in terms of convergence rates and so on. Just want to mention here also other people have thought about similar things before and after. Here's an example of such a thing. Suppose your function, a mistake says, so your function has 3 variables, so x1 is never taken, so that's not very clever. Say it's just x2 and x3, but then we can write it in such a form. Then you see that in this interior bit, each of these component functions just takes 1 variable, although in total there's a set of 3 variables, so that means the t0 is equal to 1. X1 is not here, so and the d0 is equal to 2. So you reduce by 1, but if you think about additive functions or so, you can reduce from d a d to 1, and d can be maybe at 100, and t0 can be 1 or so. Okay, so now this is this result, and I try to put it on one slide. It's was in this article in 2020, which appeared in 2020. And it says the following. It comes under certain conditions. The first one is you take the depth of the network to be log the sample size. Okay, so you see here scaling of the network architecture in terms of the sample size. I discussed it later. The second thing is you can make your network as wide as you want. So there's always this thing about over-parameterization, that your networks can have more parameters than sample size. So there's no boundary on the number of neurons that you put into a layer. The crucial thing that drives everything, the crucial thing is that the network sparsity, that this scales of a very, very specific order that depends on parameters that you probably don't know. So we call it the non-adaptive case and non-parametric statistic. They depend on these Ti, beta I stars and so, but it's just on these coefficients, not on the function itself, right? So just basically one number here that tells you something about the complexity of the function class. And you have to calibrate, somehow you have to calibrate your network sparsity and number of non-zero parameters in your network of this order. I also will discuss this later. Okay, these two assumptions. Now the conclusion is then that for any network reconstruction method, right, we're talking about methods that take the sample, the training sample, and spit out a neural network in this class with these conditions. We can say that the generalization error, which are here called prediction error, is upper and lower bounded up to log n factors by 2 terms. Okay, and so what are these 2 terms? Maybe let me start with the delta n first. What is the delta n? The delta n measures the optimization error. So basically, on Friday we also talk about this energy landscape. So we can think about the map for theta maps to f to the risk. And here we take least squares loss. Okay, sorry. So this should be this least squares loss. Okay, so we look at, given the parameter theta. So here's the theta. What loss do we have for that one? What training loss? And that gives us, because it's a non-convex problem, it has maybe many local minima and so on. So that's like I just can draw it in one dimension, but you should think about theta to be 20 million dimensional parameter, right? And you get a very maybe complex loss surface. Now, what this delta n measures is how far you get down with your method in this energy landscape. So here, say the global minimum, and maybe your method ends up in this local minimum. Okay. So this is the global one, which, because it's not computable, so you won't find it, you maybe start with your gradient descent somewhere here, and then gradient descent will bring down will bring you down in this valley to this point over here. Okay, so it's local minimum. Now, what the delta n measures is the distance between the energy of the where you end up and the minimum energy in this thing. Okay, so that's the delta n. And if you, for instance, end up in the empirical risk minimizer, then you have the delta n will be 0, right? So if you never train anything and just start somewhere, and then you're probably very, very large. And in this case, the delta n can then also dominate your rate because it's an upper and a lower bound to these log n factors. So you want to have the delta n to be small such that the statistical bound dominates, and the statistical error bound is given by that one, right? This has to do with what is now called optimization error. And it's really nice that you can bring it down to one number, which just, and it's also not about the location of these parameters, right? It doesn't matter whether this one is far away from that one. It's really like how far down they get in the energy landscape. And gradient descent always tries to go as deep in the energy landscape as possible. All the gradient descent methods basically try to to bring down the delta n, because if you have a specific one like Adam or so, you don't know how to optimize it. Okay, and then we have the statistical error bound. And the statistical error bound, we know it's the optimal rate, well, we proved that it's the optimal rate over all methods. So it's definitely a lower bound for that one. And you can also show that these neural networks, they can achieve this convergence rate. And now I'm a bit out of time for today. There are many things one can discuss about that result, the depth being like log n, that is, if you think back about the approximation results. So in every layer, we double the number of linear pieces. So if you have log n layers, you can produce a polynomial number of linear pieces in your value networks in the sample size. So that's where that basically comes from. And also the sparsity, I think that's very important to discuss. Where does that come from? There's more and more on sparsity nowadays. It's definitely taking momentum, but the problem is that these existing hardware does not allow us really to train sparse neural networks. But there's a bit of claim that they are more robust. People do that as a pre-processing, as a post-processing step to prune networks. Very good compression rates nowadays. There's some people who claim that out of 200 parameters, you can remove 199 without deteriorating the performance of your network. And so that is very natural out of the theory, but it's very hard to test and practice this thing. Maybe you've ever read about this paper about the winning lottery hypothesis, and it has also to do with the sparsity. I think it's also 5,000 citations by now, and so that's definitely something to be discussed. Also, the biological networks are sparsely connected, and that matters a lot on their learning abilities, like how sparsely they are connected in terms of how well they can generalize compared to memorization, and many other things one can discuss about that. Now, I have to jump a bit over this. Here are some examples for like standard non-parametric classes. They all can be embedded into this more general framework of compositional sparsity. And here's how we proved that via these Orcal inequalities again. These VC bounds, they're closely connected. They're closely connected. I leave these slides. I mean, you can download them, you can look at them. But we have to jump a bit in the material because next time we want to go to the learning. And in the VC dimensions, also you find that in the lower bounds, this bit encoding, which we have seen for Kolmogorov-Arnold representation, that also comes back. And what is also interesting in this VC dimensions, that somehow bound to stochastic errors. Yeah.
S is the total number of parameters.
S is the total number of parameters.
And L is just the depth as usual.
As it is the depth, yeah. So one thing which is really strange about this bound is that all these VC dimension bounds that we typically know of, the VC dimension is always bounded by the number of parameters. But here it's also bounded by the number of parameters times the depth, right? Like every parameter gives you 1 degree of freedom, and it allows you to set a somehow larger set, and that's just how it goes. But here the depth also has an additional role, such that we have very, very deep network, and that can increase the VC dimension. Many, many interesting things.